Number 4. What? Also 3? Can I see, anybody have the assignment sheet? Thanks.
On number 3, can you just explain the correlation between the box and where it's actually
Yes.
what space did we calculate for?
Okay. So number 3, we have this stress element. These two stresses have to be the same. They have magnitudes of 15 MPa. This one has to be balanced by this one. What we're doing with these shear stresses is balancing the moments so that this little element isn't rotating. So 2 MPa for each of those. And then there's one normal stress, 25 MPa. And that's balanced by a normal stress going the other direction on the negative face, but I never draw those because these stresses drawn on the positive faces is enough to know what the other ones have to be. All right, so what's the stress tensor at this point? So the first row is the traction on the positive x face. So on the positive x face, we have 25 MPa in the, oh, and here's the coordinate system. Okay, so we have 25 megapascals in the positive x direction. We have nothing on the x face in the y direction. And then in the negative z direction, we have one that's 2 megapascals. So negative 2 MPa. And then this is a symmetric matrix, so we know this one has to be 0, but we can also see that by, so now we're on the y face. And on the y face, there's nothing in the x direction, nothing in the y direction, and there's 15 megapascals in the positive z direction. And then on the z face, we have 2 megapascals in the negative x direction. That's also required by symmetry. We have 15 megapascals in the positive y direction, and that's also required by symmetry. And then nothing in the z direction. So this is the tractions on the x face. This is the traction vector on the y face. And this is the traction vector on the z face. Okay, so now we're looking for the traction vector on like the hypotenuse of this. So imagine that this stress is going on at every point in this solid shape. Okay, there's a.
So wouldn't the traction vector on the x face be 25, 0, 0?
No, because there's this one going back. That's in the negative z direction.
But don't we multiply by the face, the normal vector of the face, which was 1, 0, 0?
You, if you took this stress tensor and multiplied it by the outward facing normal 1, 0, 0, you would get 25, 0, negative 2. Okay, let's do that.
25 0.
No. No!
You don't have to.
You would not! So 25, 0, negative 2, 0, 0, 0, negative 2, 15, 0. Yes, thank you. 15. And then to find the traction on the positive x face, you do this. And you'd get 25 plus 0, and then 0 plus 0 plus 0, and then negative 2 plus 0 plus 0. What happened here? Okay, and then part B, we want to know, so trying to draw this in 3D is risky. That's not too bad. So in a coordinate system like this, we want to know what the traction vector is on this face. Okay, that's part B. So,
Traction vector is synonymous with distributed load.
yes, it's a distributed load vector. That's right. Although, if you, like in statics, all our distributed loads were just distributed over a length. These are distributed over an area, but it's the same idea. Yep.
You're just not drawing the rest of the cube?
The cube that we drew is infinitesimal, somewhere like every point in this macroscopic body has a stress cube like this. Okay, so we're assuming that inside this body everything has this stress tensor. What? It's zoomed out, yeah. Because remember, every one of those stress elements is infinitesimal. It just represents a point.
So do we think of it like the cube is then rotated, or do we think of it like the cube is like?
If you rotated the cube, it's hard to think about it in terms of those cubes represent points. Okay, so really those points don't have any shape. Think of that cube as like a mathematical. It's just a mathematical shape, mathematical representation of something that happens at a point. Okay, so the fact that this point has a stress cube like this doesn't mean that there's any kind of cube, actual cube associated with that point. That's just what's happening at that point. Just like you could say, just like you could draw arrows out of the top and say those represent the forces on that point. That doesn't mean that there's actually arrows coming out of it. Have you understood that in the past about vectors? Okay, well.
I always pictured it. If you drew the cube like right at the face,
Mm-hmm.
what would it look like?
It would look just like this.
Like a cube.
Yeah. Because that cube, it's like, you could think of drawing a cube that actually poked out of the face and then we're limiting it, taking a limit as it.
Like slicing it.
You're not really slicing it, you're just taking a limit as the lengths get smaller and smaller.
So you want to know if he's like rotating the cube.
So like the
So you're asking,
Mhm.
right? Not if it's just straight up and down.
If you rotating that cube has the effect of rotating the coordinate system, so no, we're not doing that. We will do that later. But here that cube is just a representation of the points on the surface. Anyone else have questions about that? So this, I mean, these tensors are just like a new mathematical object. Like you could have, like, if you wanted to represent the temperature along the surface, at every point you'd have a number representing it. You know, if you wanted to represent the traction at every point on the surface, you'd have a vector at every point representing it. If you want to represent the stress at every point on the surface, you have a stress tensor representing it. But that cube is just a mathematical thing. That it's a mathematically associated with the stress tensor. That's all it is, not a physical thing.
And then to solve, we multiply the stress tensor by the normal vector,
Right.
not base.
Yes. So our stress tensor is 25, 0, negative 2, 0, 0, 15, negative 2, 15, 0. And then a normal coming off of there, that's going to be 120. So it looks like that's going to be
120.
positive 0.8, yeah, right, 0.866, negative 0.50, I think, is the unit vector there. Okay. And so then if you multiply those out, you get 12.5, 0, and then can someone multiply that last set?
13.9.
Positive? 14.98?
Not important.
Oh,
Negative 12.5.
what? Oh, yeah, negative, right. It's got to be. Okay. And so if all the points, it doesn't, I said all the points inside this shape have that same stress tensor. That doesn't even have to be the case. It's just all the points along this surface have this stress tensor. Then that means that the traction on that surface, the traction vector at every point on that surface is this. And traction is something that's a little easier to, I think the only reason that it's easier to visualize traction is because it's more similar to what how you're used to thinking about things. Tensors aren't you're not very used to thinking of tensors yet, but those are just two different ways to characterize the loading that's happening along that surface.
Because my problem is I was trying to think of it like that vector that we just came up with, what base on the cube is that? Is what I was.
Right.
How I was trying to
That's
think
right.
of it, but that's not really a base.
That's not really
That's-
that's not really what it is. Yeah, because each one of those faces on the cube is aligned with an axis of the coordinate system. But okay, I think that's about all there is to that one. Any other questions about that one?
How did you get the normal vector?
I went like this. Oh, this is like my favorite topic. Okay, so this is 30 degrees, and we're just trying to come up with a unit vector in that direction, right? And so the way I think of that is I start on the positive x-axis, and then I just rotate steps at a time. Counterclockwise is positive, clockwise is negative, until I get in the direction I want. So I start here at 0 degrees, plus 30, and then plus another 90, so 120. So that unit vector is cosine and sine of 120. Okay, and then number 4. All right, so you have a bar, this is a side view. This angle is 70 degrees. And the cross section is circular. Which means that if you're looking this way at that okay, if you're looking this way, what's the shape that you see there? Some kind of oval. I'm not sure if it's an ellipse, but it's a round thing that's taller than, it might be an ellipse, I don't know. It probably is, actually. Conic sections and all. It's probably an ellipse. It is an ellipse. Okay. But it's taller than it is wide. Okay, so in order to represent the traction there, we need to figure out what the area is. And so how do you figure out the area of that shape? Yep.
Well, the area of the oval or whatever it is, it's basically pi times b times a, where b is just the radius of our circle, and a is going to be half of the hypotenuse of that.
Okay. I didn't remember that or think of that.
We had to look it up. So.
What?
We didn't either.
Yeah. But here's how I thought about it. If you think of, so if you're trying to, so imagine two shapes, okay? Okay, no, don't start there. Start here. First think of this triangle, okay? So this is the diameter of the circle. It's 0.04. No. Yeah, but that's not how I want to think about it. Just think of this as being h, this height h, okay? And this angle is 70 degrees. Then what's the hypotenuse? Well, sine of 70 degrees is equal to this length over this. So you get so it's going to be 1 divided by 0.94, you know, the sine of 70 degrees. And that is like, can someone divide that out? What's 1 divided by 0.94?
1.064.
Okay, so 1.064h. Okay. And then think about, we're trying to compare the area of a circular shape to the area of this ellipse. Okay. Where this is h and this is 1.064h. Okay. And one way you could do that is integrating. So just think that at every x value, okay, this is how I thought about it. It's a very roundabout way to do it, I think. But at every x value, the height of the ellipse is 1.064 times the height of the circle. Right? That makes sense, doesn't it? And so to calculate the area of that circular shape, you'd take the integral of 0.04 squared minus x squared square root dx, right? That for any x value, that gives you the height of that shape. Okay? I mean, we're breaking it up into infinitesimal strips. You don't even, there's not any reason for us to be going through this except that I thought through it, and so now I'm going to make you do it too. Okay, so this expression here, the integrand, just gives you the area of one of those infinitesimal strips. And so these infinitesimal strips are just 1.064 times this one. Okay. And so you can pull the 1.064 out, and you just get that the area is 1.064 bigger. Okay.
How it's an oval.
I'll bet you are. I'll bet you are. Yeah, so think of it like this is, it looks like a circle. If you cut out a shape like this out of this bar, and you sliced it just like this, the cross-section you'd see would be a circle. If you cut it at an angle, this hypotenuse is bigger than this, so the height has to be bigger than just the circular diameter, but the width doesn't change. So you have a normal diameter for the width and something more than the diameter for the height. So it's like it's an oval shape.
When you wrote this, did you take that into account, or did you just assume we do it as a circle?
When I wrote it, right, I don't have any interest in you guys doing geometry like this. I wish I'd written it as a square cross-section, and then it's just it's a rectangle. Everyone can agree to that, and it's easy to calculate the area. I just want you to understand the thing about the tractions and the, the relationship between the tractions and the stress tensor. I don't care about this geometry. Okay. But all this says that the area of the ellipse is 1.064 times the area of the circle. So the traction vector is negative 12,000 divided by 1.064 times pi times 0.002 squared. Can someone calculate that? Sorry, that's just the...
Negative 9.733.
Okay. And then 0, 0. Okay, so now we're going to use this to put restrictions on the stress tensor. So we're going to start out with the most general stress tensor. And then we'll multiply that by the normal vector to the face. So what's the...
It's actually different.
What?
You did it a different way. I thought it would be the same.
Oh.
8.97.
Okay. 8.978.
8.97 MPa.
Okay. Okay. And then, so to relate the stress tensor to this traction, we need to know the outward-facing normal. So that means we have to figure out a unit vector in that direction. So what's the angle that we want there? Positive 20. So you could go, here's 0, positive 180, subtract 70. So now you're at positive 110. Then subtract 90, and you're going the way you want, and you're at positive 20. So cosine and sine of 20 degrees is 0.940, 0.342, bless you, 0. And the relationship between traction and the stress tensor says that has to equal negative 8.97 times 10 to the 6, 0, 0. And so do this matrix multiplication, and you get that 0.940 sigma xx plus 0.342 sigma xy is equal to negative 8.97 times 10 to the 6. And second, 0.940 sigma xy plus 0.342 sigma yy is equal to 0. Oh, and then a third one. 0.940 sigma xz plus 0.342 sigma yz is equal to 0. Okay, so you can't pin down the whole stress tensor. You could pin down the whole stress tensor if you had 6 equations. We have 3 of them, and hopefully in whatever calculation follows this, those 3 extra equations will be enough to pin down the whole stress tensor.
So that's what you want?
That's all, yep, that's all you can figure out. You could figure out, so you could use this to test values. If you had values you wanted to guess or whatever, you could test whether they met this criteria, but that's the final answer there. Any other questions about that one? Any other questions? These 50-minute classes go so fast. All right, well, let me say a little bit about strain. Whose is this? Is it? Okay, so now we're going to talk about strain. Stress is a measure of internal loading at a point. Strain is a measure of deformation at a point. And before I get started with this, one thing you need to remember is I'm going to, since the pictures I'm drawing are meant to illustrate a deformation, I'm going to draw big enough deformations for you to see them, you know. But remember that we're dealing with our methods are valid only for very small deformations. So like around 0.01% of the object's length or less. Okay, so obviously I can't draw with that kind of precision, and if I could, you wouldn't be able to see what the deformation is. So I'm not going to draw things like that. So just remember that the drawings I'm going to do are totally out of whack with the size of deformations that we're capable of dealing with. Okay. So my drawings will make the deformations look much bigger. Okay, so our allowable materials have a linear relationship between stress and strain. And people call them Hookean materials because they satisfy Hooke's law. And in general, when you have that linear relationship, a stress element that is initially a cube deforms into a parallelepiped. Anyone remember what a parallelepiped is? What are the requirements of a parallelepiped? Each face is a parallelogram. And so our deformations are going to deal with length changes and angle changes. So we'll deal with changes in side length, edge length, and the length of sides, and we'll deal with changes in the angle between sides. The changes in the length of the sides are going to be represented with normal strains. And the changes in the angles between sides are going to be represented by the shear strains. Okay, so first I'm going to talk about the normal strains. So if you have an object that goes from, I guess let's make it a square. Where your x-axis is that way, your y-axis is that way, your z-axis is out of the page. And let's say that the initial lengths of both of these are just capital L sub 0. And then after the deformation, you have a new shape with a y side length of lowercase ly and an x side length of lowercase lx. Then the x, the normal strain xx is Lx minus L sub 0 divided by L sub 0. Or another way you can think of that is the change in the length of the change in the length along x divided by the initial length. Epsilon yy, the yy strain is Ly minus L sub 0. There's no surprises here, you know, they're all just the same, just using the x or y or z length. So that's the change in the y length divided by L sub 0. And then same thing with z. Okay, so if you get a positive value for a normal strain, does that mean the object is stretched or that it contracts? Stretched, yep. So positive normal strain means the object is stretched along that axis. Do you remember? So maybe you can visualize it even with the stress cube. A positive normal stress, does that mean the material is put into tension or compression? Tension, yep. So if you have a positive normal, I just wrote normal with 2 L's. Okay, positive, no, yeah, exactly. Positive normal stress means tension. So there's a sort of a natural relationship between those two, because something in tension is going to stretch. And a negative normal strain means contraction. A negative normal stress means compression. So those sign conventions, you know, they agree with each other, sort of. All right, so if you have a material that starts out with a length of 0.01 meters and a height of 0.008 meters, and you're using a coordinate system like this. And after the deformation, you end up with a horizontal length of 0.005 meters and a height of 0.011 meters. And let's say the thickness into the page stays the same. What's the normal strain? Sigma x, not sigma, strain XX is Lx minus L sub 0 divided by L sub 0. So that's, okay. And I did this funny coordinate system. So XX, okay, so this example is sort of designed to make you think about what direction these contractions and this stretching is happening for. So what matters in each of these cases, so if you're dealing with the x component of the normal strain, what matters is the stretching or contraction along that axis. So if the x-axis is, I guess it would be coming out of the page towards us here, what kind of change in length do we have along the x-axis? 0, right? We have, so it's like, we don't even know what it is, but we know that it stays the same. And divided by Lx, so you end up with 0 strain in the x direction. Okay, now are the two that we have values for. Y. This one is, in the y direction, it's getting longer. It's stretching. So we expect to have a positive value for the y strain. And we get 0.011 minus 0.008 divided by 0.008. So that's 0.003 over 0.008, which is 0.375. Yeah. No, you weren't. What are the units? Think about the units on this. Yeah, the units cancel out. So this is just a pure number. So no matter what system of units you're doing, your stresses in, your strains are the same. This is a super high. So the strains we're going to get are 10 to the minus 4 and stuff. This doesn't make any sense for the materials we're dealing with, but it's just an example. What? Yeah, right, but we can't do rubber bands because they're nonlinear. So too big for our assumptions by a lot. Okay.
Will you be doing these kind of things in the finite elements? Or no? Because there are so many assumptions for deform.
Yeah.
In finite elements, can we go more down?
Well, you can, the first class you take in finite elements, you basically make these same assumptions. You can just do more complicated geometries. But then there are finite element ways around all of those assumptions, but then it gets much more complicated. So then the ZZ strain, in the Z direction, does it stretch or contract? Contract, so what sign are we going to get? Negative. So negative 0.005 minus 0.01 divided by 0.01 gives negative 0.5, right? Yeah, why did I do that? That doesn't make any sense. Okay, so, and the answer is negative 0.5, which again doesn't make any physical sense for our stuff, but mathematically that's what you get.
Because it would like broke by that point, or things act differently after 10 years?
Because, yes, the kind of materials that we're dealing with would have broken long before that. And also, any material that didn't break before that would not be behaving linearly anymore. So that assumption wouldn't hold. And no, I mean it would deform like a piece of steel or something. It'll deform elastically, and we're dealing with things that are elastic. Like if you let go of them, they'll return back to their original shape. Like a piece of steel elastically will, I don't know exactly what it is, but around a strain of 1 times 10 to the minus 4, you'll get permanent deformations. And then we're, at that point, it won't break apart yet or anything, but at that point our calculations don't have any validity anymore. It usually gets, it's that actually, when it deforms permanently, that's called plasticity, and so it's just not elastic anymore. But at least for a lot of materials, for metals, when it stops being elastic is around the time that it stops behaving linearly anyways. That's just a coincidence. There's no reason that has to be the case, but both of those things go wrong around the same time. And then the last thing that goes wrong when deformations get too big is the superposition principle that says, so if you have 100 different loads acting on something, you don't have to treat those all at once. You can do 100 different calculations acting like that load is happening alone, okay? And for small deformations, you can do 100 different calculations and then add up the results, and that gives you a good approximation of the final result. With big deformations, it doesn't work that way at all, because like as the angles start to change, I think the easiest way to understand it is, so if this is the x-axis and this is the object that's deforming, if you do something that changes the orientation of a material element this much, okay, and then stretches it this way, doing your calculations and think you'd still be treating the stretching as if it's happening along the x direction, but that's closer to the y direction now, you know what I mean? And so things go all haywire when the angles change. Well, that's one of the reasons superposition doesn't apply anymore. But okay. Have a good weekend. We didn't get very far today.